Greetings and welcome to the pod. My name is Mark West. Professor Matthew England is Australia's leading ocean modeller and the world's foremost authority on modelling of the Southern Ocean. He's also an ocean swimmer and surfer from way back. Matthew researches the future health of our oceans under pressures such as climate change and pollution. We also talked about the mysterious tar balls that washed up on Sydney beaches in 2024 and messages in a bottle thrown overboard finding the right people. I started by asking Matthew the usual questions.
Oh, look, yeah, it's how I got in the field. If I go right back to the early days, my mum was one of these tough nuts who sort of wanted her kids to do sport, and so she got us swimming laps in a training at Ryde Pool with Forbes Carlisle as like 7, 8 year olds doing laps at ungodly hours in the morning, and I came back to a bit in my teens, but dropped it again till pretty much. Oh, actually, no, it was always around, but I really got back into it in my late 20s. I started swimming a lot during my PhD, and then got into master swimming and started doing open water swims and joined the sort of the race circuits that would be through Melbourne for a while and also Sydney more recently. Anyway, so yeah, for that 30 years later, I'm still swimming, but I did have a bit of a shoulder injury a couple of years ago that has impacted me a bit, which has been a big disappointment because I've been used to board riding as well and swimming, and suddenly I just don't have the same pain-free swims I used to have. So
Yeah. Oh, that's a shame. But you still enjoy getting out and swimming when you can?
every day
Every
I
day.
try to go, yeah, when I can. How about you?
I don't do it nearly as much as I would like to. We used to have, I mean, I live in Canterbury, and
Oh,
so
that's
there's no
harder, yeah.
beach next door. And we had the local pool, which was great, but that's been closed because they're upgrading it. So
Yeah, okay, yeah.
not as much as I would like to. But I kind of try to do that Sydney circuit ocean swims that are out there.
Yeah, nice. Yeah, no, it's good.
I'm enthusiastic.
Such
I'm not very good, but
no, but it's such a good thing for your brain to have that sort of space physically and mentally. Um, yeah, no, it's fantastic. I'm wishing you all the best for your Hawaiian trip too. I haven't been there much in the last couple of years, but we did a sabbatical. I took my kids over there, and they went to school over at Kailua, and
oh, wow.
so and then for the first couple of years after having been there for 6 months, we sort of go back every opportunity.
Yep.
And December, January, that sort of our summer became our preferred time to go because there's the big waves on the North Shore, so you can go
Yep.
see, if you're lucky, you can go see some fun surfing up there when the waves are big. And I would never go out in those conditions. They're just insane. But yeah, I hope you have a great trip.
Oh, it'll be fabulous. That sounds like a perfect place to go for an oceanographer then, as a sabbatical.
Yeah, no, it was. Yeah. I mean, the funny thing is, though, for oceanography, there are outstanding oceanographers who've never even seen the sea. They've just, got out their equations. The physics of the oceans are sort of maths problem, really. You've got
Yep.
a fluid on a sphere that's rotating. It's a stratified fluid. You can write down equations that govern the flow and start to solve them. And, theoreticians have made lots of progress on ocean circulation without necessarily even, going into the ocean. They just get these equations and play around with them. And I
Yeah.
mean, that said, I think a lot of people get a lot more knowledge from going and making measurements. Clearly, that helps. But
And is that how you got into oceanography and climate modeling, just through your love of the ocean?
yeah, absolutely. Yeah, when I was at university, I was doing maths and computing science and physics, and I hadn't really thought too much about what I wanted to do as a 18-year-old at university, which sounds silly. You think you'd actually choose your vocation. But I left school, and I knew I wanted to go to university, but I didn't have much of an idea of where I wanted it to take me from a career perspective. I had years earlier dreamed of being a marine biologist, but I never did biology. So I was kind of languishing in this degree, doing actually getting into some pure maths. I forget what your field of research is, by the way. Let me know.
Oh, mine was I did science at Sydney Uni as well, but it was
Yeah. Okay.
chemistry. Yeah.
Yeah. Okay. Yeah. I did first year chemistry too. So, but uh, in this degree, I was kind of thinking, where's this going to? And I literally flicked through the handbook and saw a picture of a wave, a guy riding a wave, and I thought, those handbooks back in the '80s were pretty boring doc. It was like a phone book where you'd open up and there were hundreds and hundreds of courses, and it was not, a little write up on each. It was not really interactive like some of the websites are today. But when I saw this wave, I thought, what on earth is a wave? So I looked at the little caption said physical oceanography, the study of the physics of the oceans. I thought, wow, that could probably work for me because I've done maths and physics, and I love the idea of studying the oceans. And I literally found it by accident, but it combined my love of the oceans and surfing and swimming with what I was studying, and actually gave me the perfect escape route out of a pure maths degree, which
Yeah.
I loved the maths, but I found myself, it just didn't feel like it felt like a very esoteric study. I mean, I knew there's huge applications for mathematical sciences, and I understand all that, but it still felt like I was studying something, or studying subjects that were not sort of so real world applicable. Um, and that's where I found oceanography. Yeah, and it was from that point I was sent on ocean voyages to go make measurements, and that was another big hook for me to sort of suddenly be traveling around the world, like literally, you know, as a 20-year-old being flown to Tahiti to join a research vessel that would then trek across the Pacific Ocean for 60 days. And it's hard work to do that, to be at sea for so long is also, at times, really challenging to be away from land. But the adventurous side of those research voyages was, amazing for me to suddenly be in that field. So I think the combination of loving the ocean and then having the maths and physics background to take on the subjects that we had, I feel like it's been a completely fortuitous accident that I landed into the field.
Oh, that's magic though. Being flown
Yeah.
to Tahiti, and so I know you do a bit of Antarctic modeling as well. Have you been flown to Antarctica?
Well, my trip to Antarctica was less fun as a flight would be.
Yeah.
I got in a research vessel in Hobart, and we just trekked as far south as we could. The sea was
Oh,
absolutely insanely stormy. We had At one point we had 2 days of just it's not sailing, basically motoring into
yeah.
the wind and the storm system, and on alert for an emergency evacuation because it was so rough, and the boat was not that big too. It was back in the in the late '80s, so there's certainly these days the best way to get to Antarctica is either to fly down there and then get onto the continent. Casey's got a runway. There are other runways there as well, or you get a research vessel that crosses the Southern Ocean and gets into the ice region. Because once you're in the ice region, it's beautifully calm
You get
as well. But
tempted to
yeah,
swim?
I would love to. I quite like cold water, but it would be a unique experience to jump into 1 degree Celsius water.
Yeah.
Um, there is one guy who I saw once who basically could do this by overheating he basically would make his body temperature through sort of exercises beforehand, raise his body temperature by a couple of degrees, then jump in, and he could swim a kilometer
Yeah.
in near freezing water. And he progressively, his core body temperature eventually got cold enough that he was just on the verge of hypothermia and jump
And
out.
you
So
jump out. That's one way to do it. I mean, you can't get it wrong. You've got to,
no,
you got
for
to
me,
do
I
it.
think I'd jump in, experience the coldness, and get straight out again.
Yeah, yeah, yeah.
Yeah.
So do you still do these sorts of things, or do you send your students down to do this crazy
Yeah,
stuff?
I haven't been. It's harder. It's harder to go away now. When I was in my 20s, I did multiple research cruises. One in the South Atlantic, one right across the Pacific, and then one in the Southern Ocean. These trips are months away at a time. They're so important. That's how we make the direct measurements of the ocean. We have satellites that measure the sea surface. We have robotic floats that can profile, but to sort of get a dedicated survey of the ocean, you need these research vessels there. But the problem is it's 2 months away, and for the last 20 years, I mean, my kids are in their early 20s now, so I as a dad who cares for their kids to go away for 3 months at a time, hasn't really been possible or attractive since my 20s. Having said that, they're now growing up, and occasionally I think, oh, I'd love to go to sea again to have that experience. But it's super hard work, and you're right. We do have a lot of students who have that time and to go on the voyages. So typically, the cruise personnel these days, a lot of early career scientists on board. Typically, only one or two people who are at the more senior stage of their careers, and then a lot of enthusiastic early career scientists who want to go
Yeah.
to sea for 60 days.
Yeah.
They've got no problems doing that. And certainly, I mean, my students that go down to Antarctica or that go on these cruises, they come back absolutely so motivated to keep in the field. It transforms their, from just say running models to go in, making the measurements. It brings a perspective of their studies that they just can't get from looking at a computer model, as good as those computer models have gotten.
Can they see? I mean, we can talk about this, but can you see if you when you visit Antarctica? Can you see the changes from year to year or 5 years to 5 years?
Yeah, no, there's big changes from year to year, and actually big changes from week to week with storm systems that come in, or you suddenly get a really mild, clear couple of days with unusually warm temperatures. There's been some heat waves down there that have come along,
Yeah, right.
30
Yeah.
degrees above average, incredible anomalies in temperature. Same for the Arctic, but progressively over time, there's certainly been gradual warming, and particularly in the West Antarctic, sea ice, as you might have heard, actually was, if anything, growing around parts of the Ross Sea, especially over the last couple of decades until about 2014. It reached a maximum, and then we've had a couple of big declines. One in 2015-16, it just went back to the lowest values on record, and then again in 2023. So it looks like after a few decades of sort of um, bucking the trend that we had projected would happen under global warming, the decline over the last decade has us on track to match what the models are suggesting, which is that the Antarctic sea ice would melt progressively. I mean, there'll still be ice there in winter, but the extent of it has come down by a massive amount. A couple of we talk in units of millions of square kilometers of sea ice. There's about 17, 18 in the average winter. We're getting anomalies of about 2 million kilometers squared, which is a big
That's a
reduction in
big
ice
number.
extent. Yeah.
Yeah. And what sort of effect does that have? That's an awful lot of water to be putting back into the ocean.
Yeah, so the actual melting or the melting of the ice, freshens the surface layer. It makes the surface layer, what we would call the mixed layer at the surface, becomes quite shallow, and so you have a thin lens of fresh water at the surface, which can have effect on the circulation. There's actually, as chance would have it, there's a paper out in Nature today talking about the effect of this ice decline, and one of the things they talk about is once you reduce the ice, the ocean then can lose heat to the atmosphere, and they found that there's sort of increased storminess at the edge of the ice zone because of this heat flux coming out of the ocean, and that's potentially amplifying feedback because storms, they break up the ice a bit more, and so it can lead to more ice decline. But yeah, the bigger change there around the Antarctic margin is that the ice sheets, so that's the ice actually sitting on the land, as opposed to the sea ice, which is the stuff that just forms every winter and then melts in summer. That sea ice doesn't raise sea levels, but the ice that sits on the land mass, basically when that flows into the ocean, it raises sea levels, and it's also freshening the waters and making the oceans again more buoyant. So that fresh lens makes the water less dense than it should be, and that means that overturning circulation can slow down. We had a paper out about this early 2023. We hear a lot about the AMOC, the North Atlantic, slowing down, but we have an overturning circulation off Antarctica that's just as vigorous and just as important to our climate system, and probably already twice the slowdown of the North Atlantic
Oh, wow.
overturning.
Do we just hear more about the North because there's more people up there and so more people study it?
100%. Yeah,
Right.
it's we've got paleo proxy records for the North Atlantic overturning. We've got ships that cross between Europe and North America that have been measuring the conditions up there for 50, 60 years with pretty good resolution. So there's way more data. There's way more people that care about it. The neighboring, you know, the amount of ocean measurement scales with the basically the wealth of a nation. It takes a lot of money to go make ocean measurements. So the ocean measuring globally has been led by the Europeans and the North Americans, US in particular. Nowadays, China, India, and other places are picking up some of that observing, but still a very big Northern Hemisphere bias to the measurements. So we just don't have the same number of measurements around Antarctica. And unfortunately, what we're seeing when we do get the measurements back, they're coming back with much warmer conditions up at the ice margin than people have expected. So um, with literally some of the ice shelf fronts have never had the ocean temperatures measured there before. And so when a cruise goes down and makes a measurement, there's a certain expectation about what the temperatures might look like. And virtually every cruise comes back with data that shows much warmer water than we expected to be there. Now, unfortunately, if it's the first ever measurement, we don't know if that's now, much warmer than it was 20 years ago. We just know that there's temperatures of the water there that's easily enough to melt the ice shelves, and what then becomes the challenge to understand is, is water, if we're getting warm water onto the shelf continually, that's a really bad situation because that'll keep melting the ice. If there's just a patch of warm water that's there and it's isolated, it's just an eddy that's come in, it's a once-off thing. That's not nearly as bad for the ice melt. So unfortunately, we need to basically make more measurements down there to understand what's going on.
Right. Yeah, I've read some interesting things about, mosses and whatnot being discovered down in Antarctica. It's now warm enough. There's enough land down there for things to grow on.
Yeah, there's heaps of ecological changes. The the West Antarctic in particular has about 60 more days for the coast to be ice free. So the sea ice that forms every winter basically kind of shields, in some sense, the coastline from invasive species. We're seeing more and more ice free days. And to have 60, I mean, basically, parts of the West Antarctic might have had, in years gone by, only say 50 or 60 days per year that are ice free. Now suddenly there's 120,
Yeah.
double the number of days. And that's the part of Antarctica that is most exposed to incoming flow from the north. Like if you look at the main circulation fields, the Antarctic Circumpolar Current comes very close to the coastline there. And another study out a few years ago found this seaweed that had colonized in Antarctica. Nobody thought it would be even there,
Yeah.
let alone that it could actually survive there and respawn. So there's certainly a big risk of ecological changes there as the climate changes, as things warm up. Um, we think of it as relatively isolated because this flow around the continent, the Antarctic Circumpolar Current, as the name suggests, it flows right around the continent of Antarctica, but it actually flows so fast that we think it's hard to cross. But we're finding that eddy, like the flow is very strong in an east-west sense, but a lot of turbulence and eddies form around that circulation, and that can bring patches of water south that can carry seaweed and even plastics, even pollution is being found on the
Oh,
coast around
great.
Antarctica,
Okay.
which shows us all these garbage patches that sit in the North Pacific that we thought you wouldn't see these sorts of plastics appear in Antarctica. We're finding the connectivity to Antarctica is a lot greater than what people have thought.
Wow. That's not very positive. Where does the bulk of the seaweed and the plastics go down there? Do they just sink to the bottom, or are they perpetually spinning around?
Yeah, no, they most of it hits the West Antarctic continent. So if you look at a map of Antarctica, the West Antarctic part of the continent, if you look at a map of Antarctica, you sort of think of it as basically circling the South Pole, but it's got a bit of geometry to it, and so the Ross Sea has a big ice shelf there that sort of he- cuts in south towards the South Pole. Same with the Weddell Sea around south of the Atlantic, but the Antarctic Peninsula is this bit that sticks up towards South America. and that Antarctic Peninsula section heads basically north towards the southern tip of South America, and that's the bit that's most exposed to plastic, seaweed, invasive, like other biology that sort of basically circles around the world, and it is also it's the most exposed to those northern waters. It's also the place where the temperatures have changed the most, where ice has melted back the most. So it's both exposed to those sources of water and biology, but it's also the most habitable in terms of, if a human was going to go and survive a winter in Antarctica, you pick the
That's
West
where you go.
Antarctic section because it's the warmest, the mildest climate. Yeah.
Yeah, how interesting. And what are some of the changing currents down there? Is it and would they have effect on Australia or the rest of the world?
Yeah, no, the biggest one that we think is vulnerable to change is this overturning circulation that I mentioned. So it's basically around the Antarctic margin. There are patches of water, not everywhere, but there are certain locations. There's actually four main locations where the water is so dense that it sinks to the very bottom of the ocean. Not just, around Antarctica, there's a continental shelf, so about a 100-meter deep shelf, like all the continents have, like we have off Australia. So the water sinks that 100 meters, but that's not enough. It's so dense that it actually then cascades off the shelf and sinks down to 5,000 meters. And not only does it sink down to those very deep depths, it then travels northward and actually reaches as far north as up around Hawaii. Like it reaches right into the North Pacific, into the North Indian Ocean, and actually into the North Atlantic. So this water mass that's formed even in such isolated locations around Antarctica flows off the shelf and actually ventilates the entire oceans below about 2 kilometers depth. And so this overturning circulation is such a big part of our global conveyor of water in the oceans. But unfortunately, it's quite vulnerable to change because it's only those four sites. And these four locations, one in the Weddell Sea, one in the Ross Sea, one in Pritz Bay, and then one also off the Adelie coast. Those four locations, two of them are right where the ice shelf melt water ends up. So we're seeing that water become fresher. And like I said before, if it becomes fresher, it's less dense. And so it doesn't sink. So it's this Antarctic overturning that's the main current thing change down there.
That's it's so interesting that it's kind of oh, I guess I don't know quite right the word. It's lucky that the world is as it is, that Antarctica is down there and we get these particular currents that
Yeah,
ventilate the
no,
whole
that
world.
no, exactly. That overturning I spoke about, it's so important for the health of the oceans because when the waters sink down to the bottom of the ocean, they basically then recirculate back up to the surface, and in doing so, they bring very nutrient-rich deep water back up to the surface. And so, if you think about when the water comes back up to the surface, it's very nutrient-rich, and the reason it's nutrient-rich is that all of the biology that sits at the surface of the ocean when that biological matter dies, when fish die, when zooplankton die, it sinks to the bottom of the ocean. So all this very nutrient-rich matter sinks to the bottom of the ocean, and we need the bottom currents to bring that water back to the surface and replenish the surface with nutrients. It's very different to land. When a tree dies on land, it decomposes, and the nutrients go back into growing a new tree, right? When fish die, the nutrient matter associated with that biology sinks, just rains down to the bottom of the ocean, and we rely on these deep ocean currents to bring that water back to the surface. And so this overturning circulation I spoke about, if we don't have this overturning circulation doing that recycling of nutrients for us, then we leave a lot of the nutrient rich water at the bottom of the ocean. And that means that ecosystems at the surface, they still will have nutrients. Some of the nutrients get recycled in other ways. It's not like we cut off all supply of nutrients, but we cut off about a 20 or 30% um, quantity of nutrients. And that means less phytoplankton, which means less zooplankton, which means less food for fish. So the world's fisheries are potentially going to take a hit by having this nutrient-rich water just stay stagnated at the bottom of the ocean without that flow. That's why we talk a lot about these circulations. The analogy I like to use is an aquarium. Anybody who's got an aquarium at home, if the water's stagnant and just sits there, layer upon layer, in the vertical, just not being recirculated, you tend to get a very unhealthy aquarium. The water isn't well oxygenated. The nutrients aren't well mixed through the water column. The ocean's the same. We have a global body of water that is healthy if it's circulated in a vigorous way. Now we are lucky that the things like tides will always be there. So the movement of tides actually moves water around the ocean. Even in the deep ocean, that creates some internal waves, and we do get some mixing that would play out anyway without that flow. But recirculating the nutrient rich water via that deep ocean overturning is a very critical part of the cycling of nutrient rich water in the oceans. And so to lose that flow would be a big impact on our ecosystems.
Is that something that would just turn off, or is it going to peter away, or do
No,
we
it's a
not
great
know?
question. Yeah, no, it can just turn off, which sounds dramatic. And the reason it is dramatic is that with this freshening, I say turn off, it would take decades to properly turn off. But on the scale of that overturning, it's been there in a sort of what we call an on or overturning state for thousands and thousands of years. It's been it's part of any textbook description of the ocean circulation. We think of it as prevalent or stable as the tidal circulation, to something that should always be there. So for it to turn off in a couple of decades, it can be done by this meltwater that's being added from the melting ice sheets. And the reason why I can say it just switches off like this is that we already see at the moment from our model simulations, if we have a particularly mild winter, where the temperatures aren't too cold, the density of the water that forms in that winter may not be dense enough. It doesn't get cold and salty enough to sink to the very bottom. So we already know that for a couple of winters in a row, if the conditions aren't cold enough, you don't see that overturning circulation occur. The reason why it doesn't fully collapse at that point is that you only need the overturning to happen every couple of winters to keep the machinery going, because it takes literally decades for the water to cascade down to the bottom of the ocean. So we're in a sort of on state with this overturning. Getting a cold enough winter every couple of years is plenty, but as the cold winters are drying up and as we're seeing more and more mild winters, we're seeing fewer of these vigorous overturning years. And the evidence we have from observations is this is already happening. We're probably already about 20 to 30% through a slowdown of the overturning circulation, with expectations this will get worse. And that time scale of only a couple of decades is I think surprised a lot of people. A lot of people would have thought would take centuries to slow the overturning down, but it's a highly nonlinear process because all you need is that melt water to cap off the surface density of the water mass, and it can switch off the overturning. And like I said, we can see it in any given winter. If the conditions aren't cold enough, we don't see any overturning. And as we know, with global warming progressing, winters are becoming more mild. It's not to say we won't get a nice cold winter in a couple of years' time, but the overall trend is one of warming, through the record, and that threatens this overturning circulation.
Yeah, and I guess you can't turn it back on very quickly either. If somehow we miraculously limit CO2 emissions or whatever.
Yeah, no, you can't turn it back on until you basically get back to a colder climate. And unfortunately, with CO2 emissions, when we put this carbon dioxide into the atmosphere, it basically stays there. It's not like methane. Methane, for example, it's why we don't hear much about methane. It's a much more potent greenhouse gas, but the the veg, the sequestration of methane back into the ocean and land system takes of the order of 10 years. So if we were to cut off our methane emissions today, within about 10, 15 years, we'd get that benefit of drawing methane back out of the atmosphere into the land and the ocean. Carbon dioxide takes thousands and thousands of years to sequester back into the ocean and land. The cycling of CO2 of carbon dioxide is much more slow, and you can see this in the production of coal. It takes coal millions of years to be formed out of compacted biological matter. It's a geological scale process, and so unfortunately, yeah, wherever we get to in terms of stabilizing our carbon dioxide, that'll set where our global temperatures are at, and that'll set where the Antarctic temperatures get to, which sets the ice sheet melt, which sets the overturning. So it's one of those parts of the climate system that is hard to turn around. And that's why we've been saying for a long time now, we need to, stop our emissions of carbon dioxide, get off fossil fuels, because we're basically talking about, where we stabilize the climate at. Is it going to be at the high end where we have these very costly changes, or are we going to aggressively cut the emissions and get to a climate state that still has changes that are still costly, but not nearly as bad as the high end scenarios?
Yeah, I haven't seen any new innovative carbon sequestering technology that works at any efficiency yet. I don't know. Is there anything on the horizon?
Yeah, no, it's a good thing to point out. We're used to things being solved, and that's, I love the way science has. We had COVID come along, and vaccines were. I mean, a test was done, and vaccines were found, and it's incredible what human ingenuity can solve. Unfortunately, you're right. Nothing can scale to sequester carbon. Even if we planted seaweeds in all the habitable areas of the coastal oceans, that's a drop in the ocean in terms of our emissions. I saw a study some years back where you could get something like 0.5% of global emissions, sequestered through seaweeds. Planting forests is fantastic. It can, in Australia's grassland farming has ruined our environment. Planting trees is great to do for the land system. It does draw down some carbon, not nearly enough to take account of our burning. I mean, the best way to stabilize the climate is to stop burning the fossil fuels. Some negative emissions can help. These kooky ideas with giant vacuum cleaners, where the air comes through a wind turbine and a chemical reaction takes up the CO2. I mean, the concentrations of carbon dioxide in the atmosphere are tiny. We're talking 350, 450 parts per million. These are tiny concentrations. And of course, people then say, well, if it's so tiny, how does it change our climate? Well, the radiative effects of carbon dioxide are so effective that doubling from 280 to 560, as we're on track to do, is a massive perturbation of the climate system. But as you say, we can't get that carbon dioxide out of the atmosphere very quickly. The only way that's possibly viable is through enhancement of the ocean carbon cycle through alkalinity. But a lot of people that I know are working in that area, and they're cautious about it because we don't yet know what the other consequences are. But there is some promise that you can enhance the alkalinity of the ocean and draw down carbon dioxide in the ocean without having the acidity problem that you get.
That's interesting. So, because I was going to ask you, how much more can the ocean take? But there's things we can do
Yeah.
to make more alkaline, can we?
Yeah, I mean, the oceans are basically doing everything they can to draw down that carbon dioxide. So as the carbon dioxide goes in the atmosphere, ballpark numbers for every 100 units we emit to the atmosphere, about 25 gets absorbed by the land surface, so through our forests, and then about 25 units get absorbed by the ocean. And because the oceans have this overturning, as we keep emitting, the oceans keep absorbing. So they're doing their best. The only problem is that as we warm the ocean, we basically stagnate the overturning. Warm water is less dense, so it sits at the surface and stratifies the surface ocean. And so this overturning of carbon dioxide that we want to have happen, burying it deep below the surface, we're slowing that down, and so that 25% uptake I spoke about may decline to 23%, and that's no good because we're talking about gigatons of carbon difference by having even a couple of percent decline. So the oceans, I mean, one way to put it is the oceans are doing incredible service for us at the moment. They're absorbing 25% of our carbon emissions. They're absorbing about 90%, about 92% of the anthropogenic heat that we've trapped in the system. And so you sort of think, well, that's great. They're removing the problem from the atmosphere. There's a problem, though, with them doing this. One is that we don't know that those numbers are very stable. As time goes on, the heat uptake slow, the carbon uptake will likely slow. The second thing is that they don't come free of charge. The heat uptake raises sea levels, it melts polar ice caps, it intensifies tropical cyclones, bleaches coral, it impacts ecosystems, it makes the atmosphere more humid. And we saw that off Sydney last summer. Incredibly warm Tasman Sea gave us, I think, the most humid summer we've ever had. We didn't have a particularly warm summer for the temperatures, but humidity is what really stresses the human system. Heat plus humidity is a really bad mix. And it's that warming of the ocean, warming the atmosphere from the oceans that delivers not just heat, but also extra humidity that's particularly dangerous to human health.
Yeah, it's fascinating. And I think we kind of have this image of, I don't know quite the right way to say it, but that the ocean will be fine. But it's clearly not the case. It's just that we don't see the effects. It's not an immediate effect. It builds up.
Yeah, that's right. It's so vast that you sort of and nobody's sort of going down to the ocean. Oh, gee, it's 1 degree C, 1 degree Celsius warmer today than it was 50 years ago. You just don't notice that change. But certainly, ecosystems are noticing the change. Coral reefs, the bleaching of the last year has been catastrophic for the Great Barrier Reef. To see the amount of reef bleached, and sea levels are rising, and all these other changes are playing out. So it's a bit of a slow burn process, but it's very detectable in the measurements we've made with big impacts.
What do you think will happen? Are we going to stabilize at 500 parts per million and solve all our problems?
I think we'll stabilize the climate at some point. We'll get to we will move off fossil fuels, because I think the costs of doing nothing already very clear. Doing nothing is going to be too costly. The big question is where are we going to come in at net zero by 2050? Everybody, all the major emitters pledged to that, but it's an easy pledge to make because it's so far away and the electoral cycle is very short. So my guess is that we're going to stabilize at too high a carbon dioxide level. So we will reduce our emissions. We will get down to net zero eventually, but it'll be too high a level of carbon dioxide. And so that's where some of these more extreme measures of trying to cool the climate system by browning the sky. So when jets fly up in the stratosphere and they emit some aerosols, they can basically create a reflective surface for sunlight. It sounds like a sci-fi material, but that's a very costly thing to have to do. But when you've got a climate crisis and some of these extreme events, I mean, if you look at some of the climate extremes we're seeing already at only 1 degree or so global average warming, or we're getting up towards 1.5 now. So, if you go to 3 degrees, that it's just an insane amplification of those climate extremes. And if we get to 3 degrees Celsius, I think that's where you're going to start seeing some kind of solar radiation, geoengineering, not big sheets in the sky. I've heard that put forward before, but these measures of basically browning the sky, putting some aerosols into the stratosphere.
Yeah, it's silver or sulfur or something.
Yeah.
So I'm kind of making that up. I can't remember, but
yeah, no, it's very extreme. But if you're trying to stabilize the climate or bring it back to a colder temperature, I could imagine that being pursued, but I mean, it's hard to gaze into the, I mean, the other possibility is that we find a way through this ocean alkalinity to draw down carbon dioxide. But it feels to me like if you look at the carbon dioxide trajectory, it doesn't look like it's taking the right shape to stabilize our climate at a safe level. And that's where you might see this intervention through other approaches.
Yeah, I think 2024 has finally shaken off the COVID dip, and we're back on the long term
Yeah,
uptrend, aren't we?
yeah, that's right. No, it's definitely going up at an alarming rate, and we've got countries that have still got very low emissions per capita. That under a lot of these UN agreements, those nations are if they industrialize and develop energy systems and transport systems like we've had in the US and Australia, then their emissions will surge. And all the while, the US has got a new government that are going to dig up
Drill, baby,
fossil
drill.
fuels.
Yeah.
Yeah, exactly. So they're not great signs. Having said that, there's also some good signs, and there's in Australia, for example, solar is the cheapest form of electricity. We've got an abundance of it. Adding some storage to that, battery storage, is all we need to, alongside some wind energy. There's a PhD student at UNSW who did the study and showed us going to net zero is actually cost positive. We make money out of the transition.
Yeah, cool. We put
Yeah,
solar panels on our roof a few years ago. They're just a tiny little 2 kilowatt thing because we're in a
yeah.
tiny townhouse. But yeah, we got because I'm a data nerd, Solar Analytics, or a spin off from UNSW.
Oh, fantastic.
Yeah, it's pretty cool. So we can see the curves and all that sort of stuff.
Yeah, it's amazing. And my sister went and put got a storage system as well, which when I looked into it a few years ago, somebody said to me, like, just wait a couple of years. It's probably now's the right time to, these batteries are still expensive, but um, if you look at the energy savings, you get your money back within, 3 or 4 years, you get your money back easily.
Yeah,
You 15 years, but it's now, only 3 or 4.
yeah. We kind of place a lot of hope that the market will solve all our problems, don't we? I'm kind of
Yeah.
increasingly skeptical, but can only hope, really.
Yeah, I mean, it's funny because with those technologies, that if you're too early an adopter, it can. I remember when DVDs first came out; they're like
Yep.
$1,000, and a year later they were about $80. So it's
Yep. Yeah. Oh, look, we have a beta player around here somewhere. So.
that's great. Yeah, we tend to be pretty slow too on the uptake.
Yeah, that's right. So there was another kind of topic I wanted to ask you about, and these are the fat balls or the tar balls that
Oh yeah, right.
that
Yeah,
landed on the Sydney beaches, and I was having a read of them. They were fascinating, and I noticed you got kind of interviewed about them. What did you think about that story?
yeah. No, it was amazing when they first arrived. They looked just like the tar balls that you see in the Gulf of Mexico, where not just through actual ship oil spills, but also natural oil being vented into the ocean can form these, basically the action of the waves and the winds churn over blobs of oil that sort of connect a bit with some biology and sand. I mean, when I say biology, bits of plankton and stuff, and becomes like a little floaty because of the oil, um, piece of rubbish, basically, or particulate matter all glued together through the oil. And so that's where at first, yeah, I think everybody thought it was some sort of oil spill somewhere. But what was, and I'm glad when you say something in the media, it's always go on a limb and you say what you think something has occurred. At one point, I made the comment that because it was only Coogee Beach, so isolated, it was unlikely to be an oil spill from a long distance away, because we would have seen more of, more beaches impacted. Just one beach, it must have been quite localized, and that's where I guess it was corroborated with the analysis that shows that it was out of Sydney's sewage system, basically. I don't know if you saw the follow-up reports, but they found, traces of recreational drugs in them. They found traces of stuff that meant it had to come not from an oil spill off a ship, but from oil coming through the sewage system. So it could be. I know that disposing of cooking oil and that sort of stuff can be costly to dispose of waste in the proper right way, which is a shame because we want people to not go and dig a hole and throw their asbestos sheets in there. We want people to properly dispose of waste. And my understanding is that the most likely scenario is that there's been an industrial scale dumping of oil through the sewage system, and so the outfalls had a particularly high. I mean, there would be some cooking oil that goes through the sewage system somehow, I guess, or through grey water. Who knows how it got in there at this bigger scale? But it's too much to be just the normal amount. We would have seen these tar balls before. So somebody somewhere has dumped a whole bunch of cooking oil into the system, and it's then bonded with some sewage and other stuff. So apparently they absolutely stunk. I didn't get near one, but the chemists at UNSW did the analyses, said they were just revolting to handle and to deal with. But it does go to show, these outfalls are actually 3 kilometers off the coast, I think, nowadays. But whatever we put in there, it doesn't go away. I mean, you see this with the big garbage patches of plastics, and like you said earlier on, the ocean's vast. You can think that whatever you throw in there, you won't see it again. But I think most people who go to the beach will have had that experience of getting down there some days, we used to go up to this beach up the north coast of New South Wales, miles from anywhere, but in a certain swell system, we just get the beach would be awash with a lot of junk. With it must have been from the northern hemisphere. A lot of Japanese or Korean labeled bottles and plastics, and I don't know how it made it down to the coast off just north of Coffs Harbour there. Middle of a national park, most pristine beach normally, and suddenly it's just awash with pollution that's come from a very far distance. But a lot of this stuff floats and gets blown around by the wind, and will eventually make landfall again, given enough time.
Yeah, it's kind of amazing how connected it all is. So these tar balls, yeah, they're not something that would easily biodegrade either. I imagine they'd just eventually sink. Is that what would happen?
Yeah, I think so. I think they tend to hang around, and yeah, it wouldn't any dolphin or fish that sort of went, oh, is this some food? I'll have a mouthful of that. Would have
Ugh. Yeah,
regretted it.
yeah.
But yeah, no, it is so connected. Amazing story. I mean, any point of the ocean is connected to any other point. Um, you know, Years ago there was an amazing story where a message in a bottle had been thrown off a ship, a World War II vessel somewhere in the English Channel. And what was amazing about it was that it was an Australian soldier at the time who threw the bottle over with a note, and it actually landed on the Australian shoreline within 100 kilometres of his hometown. I
Oh
forget where it was
wow.
exactly, but it was quite an amazing story, and you know, fantastic story that made it back to Australia. This message in the bottle, but I remember when it first happened, we all thought, "Oh, how did it do that?" And it didn't take us long to kind of go, "Okay, so it would have looped in with that current." And you can, of course, all the oceans are connected. They all have these large scale, sort of, um, uh, well, clockwise or anti-clockwise, but large scale gyre circulations. You could sort of basically go from point A to point B anywhere in the ocean with some circuitous journey. Um, Eventually, all of it's connected because it is one big ocean, with the land obviously breaking it up into an exotic shape. But every bit of the ocean's connected, and you literally can throw something in the ocean at some point, and it can get to the Arctic or to the Antarctic eventually, with the right bit of luck, catching a ride with the right currents and the right eddy fields.
Have you done that? Are there any letters that you've written that are out there waiting to
No,
be?
no, no. I haven't done it myself, but one of my postdocs a few years ago made a wonderful sort of website portal where you could literally click your point in the ocean where you want to see where the flow goes, and it would basically, the model simulation would show the array of trajectories that could, so basically scatter particles in this ocean model, and they would take, eventually all of the particles would spread different regions globally. but it was a wonderful demonstration of the, there are, if you drop sort of water, say in the Coral Sea, or something in the Coral Sea off the east coast of Australia, most of the flow is down the coast, off Byron Bay, down towards Sydney. It then bifurcates, heads towards New Zealand. There are sort of coherent flow fields that are there, but there's also a randomness through these eddies where you can get the flow heading off in a direction. Another one a few years ago was a surfboard. Some guy was surfing in Tasmania and somehow had a wipe out and lost his board, and it drifted off into the ocean, and it landed up on the Gold Coast. And that's completely like the flow field is actually down the coast. You have the flow coming. And so again, a lot of us, one of my colleagues went in the media and they're asking how could it have done this? And there is certainly a way the board could have headed off towards South America in the gyre and then come back and then
Oh, wow, the whole way around, yeah.
Long, it would have taken a couple of years or more, probably about 10 years.
That's
So,
cool.
yeah.
That shows you how long these things hang around for as well. I mean,
Yeah,
surfboards aren't
that's
going to
right.
break down anytime soon. What's next in the Matthew England ocean journey? Have you swum today?
Look, yes, no, I've already swum today. My daughter's getting into ocean swimming. We had a swim down at Gordons Bay. A nice summer break coming up for sure. But two of the main things I'm looking at the moment are the heat intrusions around Antarctica. We're really worried about that ice melt that I mentioned, and it's from a sort of scientific perspective, it's a very fascinating oceanographic problem. There are small scale eddies. It's a very hard region to model. There's very few observations, so it's a nice scientific challenge to work it out. But also, as I mentioned before, it's where the ice is melting, so we need to understand that flow field. And the other thing I'm working more and more on are these sort of marine heat waves, these patches of water we get where you get super warmed waters. I really looked at the North Atlantic warming from 2023 last year and same thing for the Great Barrier Reef, how to understand these huge anomalies in temperature, because we know they impact ecosystems so much. And so I'll be doing a fair bit of work on understanding those marine heat waves, both around the waters around Australia and also when they happen out in the open ocean.
Yeah, we've certainly had some around Australia over recent years, haven't we?
Yeah, one on Ningaloo a couple of years ago, and certainly the Barrier Reef is getting hit by pretty tough conditions. Really hot summer temperatures.
Does it have much left in it? It doesn't sound good for the Great Barrier Reef.
Yeah, no, the Great Barrier Reef is probably one of the the front line of climate change. For the reef has very clear temperature thresholds, and once you go past that, the reef bleaches and dies, and then you don't regrow the reef in a hurry. So I say to people, go visit the reef, get there while you can, and the tricky thing is you get, the bleaching is very patchy, so you sort of think, okay, it's going to progressively bleach from the north towards the south, but the last year's bleaching event, some of the worst hit regions were the southern parts of the reef. So yeah, that's one of the most predictable parts of climate change, these marine heat waves. And then we know the reefs have these thresholds, and unlike fish species can migrate poleward, we're seeing a lot of fish species migrate poleward. Unfortunately for a reef system, you will see reefs appearing further away as the water's warm, but they don't grow fast enough. The changes are happening too quickly to see the reefs migrate. They just can't do that.
Thank you very much to Matthew England for taking so much time to talk to us about ocean health. If you'd like any more information on anything you've heard today, get over to the website at www.thepodpodcast.net. That's www.thepodpodcast.net. And thanks again to Matthew and the listeners for bearing with me while I took about 3 months to edit this episode. There were some summer holidays in there. Hopefully I won't be as long for the next one. Take care, and I'll catch you then.